Alright, so in this video, I'm just going to talk about really quickly how to make alkenes from alcohol starting materials. So this video is just going to be about dehydration reactions with sulfuric acid. So treating in this case, a secondary alcohol with sulfuric acid. And we're gonna get three products here, as you all can see here. So we have one, two, and third product. So we have three products, and then we're gonna talk a little bit about the Zaitsev rule and we're gonna choose our major product, and we're gonna talk about why that certain product, either 1, 2, or 3, is going to be our major product based on the Zaitsev rule. But first, let me show you how you get all three products, and then we'll pick our major product. So let's go ahead and walk through this mechanism here. So I'm going to walk right through it, and I'm going to choose a different color. So let's go ahead and go with green. So the first thing I like to do, and the easiest thing to do when you're trying to solve these type of problems is, this is why Lewis structures are really, really important, because you kind of have to see what is going on here in solution. So, and if you draw the Lewis structure of sulfuric acid, which is what I just drew, you'll be able to tell that we have, so sulfuric acid has two really, really acidic protons. Sulfuric acid has a pKa of -7, plus or minus 1. So, but sulfuric acid is really, really acidic. So that proton right there has a pKa of about -7. Right there, about -7, and the pKa of this proton is about 16. So as you all can clearly see, this is going to be sulfuric acid is our acidic moiety here. So that's what we're going to use as our and on top of that, sulfuric acid is one of the 6-7 strong acids you're taught to learn in general chemistry, and so that's how we know that that's our acid in this case. So I am going to go ahead and do that. All right, and now let's go through the mechanism. So what happens? So a lone pair from the alcohol group over here on the cyclopentanol is going to grab one of sulfuric acid's protons, and it's going to get protonated. So the alcohol gets protonated, and the electrons that are attached to the hydroxyl group there on sulfuric acid, to that OH, are going to jump to that oxygen. So that's the first thing that happens. So the tail of my arrow here is coming from the lone pair of the electrons on the oxygen, on the alcohol, and it's gonna go ahead and get protonated by that sulfuric acid hydrogen right there. And then the next thing that happens is we're gonna go ahead and draw that. We draw the result of that, and so then that oxygen therefore picks up an extra proton and becomes positively charged. So now we have a positively charged oxygen right there, and that is called hydronium. So that's a hydronium ion. Okay, and let's not forget our methyl group right there. And so the next thing that happens now is this becomes right here. So this becomes a really, really good leaving group. And so that's actually what happens next, is that the leaving group, the electrons in this bond between the carbon and the oxygen of hydronium, are going to leave, and it's going to want to form water, again, because oxygen hates being positively charged. It would rather be neutral. And so that's the next thing that's going to happen in this mechanism, is that you're going to form water plus the formation of a carbocation right there, which is really, really important. So that carbocation here, really, really important. because with this carbocation, every product here is going to get formed. So this is the intermediate that we really care about. So this intermediate right here is what we're going to be working with this entire time. So go ahead and copy that down, and I'm going to go to the next slide, and I'm going to show you all what we do with this intermediate. So these are the reagents that are going to be in play now from our mechanism. All right. So here we go. We have our mechanism here. We have our intermediate. And now all I'm going to do is I'm going to play around with the carbocation. So one of the things that can happen is this. So one of the things that will happen is a hydrogen from that carbon is going to get deprotonated, and the electrons from this bond are going to jump back on there, because again, so carbon doesn't like having three bonds. That's what that carbocation means. It means that carbon's missing a bond. Again, it would rather have 8 electrons and have 4 bonds around it. So you're gonna want to try and give carbon back 4 bonds. And so that's one of the things that drives this reaction right there, is the formation of a double bond to get rid of your carbocation there. And there you go. So that's one of the product that forms. And again, you always regenerate your catalyst. So this is one of the products that forms. And which product is that? That would be that one right there. Okay, that's one of the product that forms. Another product that can form, I'm going to draw it right here, is going to be this guy right here. So what happens if I instead grab this hydrogen right there, because that's also possible. So that oxygen is going to go after that hydrogen. The electrons from this bond are going to collapse back on this carbon right there. And what is going to happen is you're going to form this instead, which that happens to be this product right here. Okay. All right. So now all we have left is this product here. We have not formed this product yet. So how does that happen? So how does that occur? So I'm going to take you all to the next slide and show you. So remember, this is our intermediate. All right. So the thing about this mechanism here is so this is a secondary carbocation, right? Secondary carbocation. However, we can form a tertiary carbocation. And how does that occur? The way that occurs is through a hydride shift. So if you get a hydride shift, this hydrogen here can switch places with the hydrogen right there. Excuse me, it can fill the void that's missing on that carbocation there. And there's already a hydrogen there, so you can give that carbon right here, you can give this carbon right here 4 bonds by doing a hydride shift. And if you do that, you are going to get this instead. Now your carbocation has moved from a secondary position to a tertiary position. So although we still have a carbocation, however, it went from being secondary to tertiary, which is way more favorable thermodynamically, at least, even though, it's still bad to have a carbocation, but thermodynamically, that tertiary carbocation is just a little bit more stable than the second one. And of course, the more stable you are in nature, the lower in energy the molecules are, and the lower in energy, the happier they are. So things tend to usually always move to a place of lower stability in nature, and that's what occurs here. So now we bring in our conjugate base here from our sulfuric acid. This is going to be that. And now we can grab any one of these hydrogens here are going to be up for grabs. So any one of those hydrogens there are going to be up for grabs. And so you grab one of those protons, and the bond from any one of these protons is going to collapse onto these two carbons right there. And what you're going to find is that you get this product right there. Okay, so that's how you get that third product right there. All right, so which one of these is going to be our major product then? So let me go back a slide. Is it going to be 1? Is it going to be 2? Or is it going to be 3? Well, according to Zaitsev's rule, the most substituted alkene is the most stable alkene. So if you all remember from lecture, the more stable, the more substituted alkene is the major product according to Zaitsev's rule. So which one of these alkenes is the most substituted alkene? So, and if you follow what you learned in lecture, you're going to get that number 1 here is the most substituted alkene. So number 1 is surrounded by 3 R groups. So this would be one of the R groups, and then that's another one, and then that's another one right there. So that's 3. Number 2 is only surrounded by 2 R groups, and number 3 as well only has 2 R groups right there. So it's only di-substituted. So 3 is di-substituted, 2 is di-substituted, 1 is tri-substituted. So because 1 is tri-substituted, that means that that's going to be your major product according to Zaitsev's rule. Remember, the major product is always the most stable one. So there you go. That's how you solve these type of problems. Go ahead and subscribe to my channel. I'm going to be doing a little more problems here. Maybe some problems that are just a little bit more complicated. I really hope this helps. Thank you.